We are going to start covering Module 14 now, which is a chapter on electric potential. He starts off this chapter by trying to explain the difference between something that we covered in the previous chapter with what we're now going to be covering in this chapter. Equation 13.1 was an equation for electrostatic force. And when we calculated that, we took this constant times both of the charges that were involved divided by the distance between them. And so if you recall, when we this constant was in Newton meter squared per Coulomb squared, and then we multiply that by two different charges. So that means that these coulombs all canceled out. And then the radius squared on the bottom was in meters, and so that meant that this one canceled out with the meters squared on the top. So we ended up with units of newtons, which makes sense since it's a force that we're actually calculating here. So newtons is measured with electrostatic force. Now he then tells you at the beginning of this chapter that the formula for finding electric potential is given by this symbol V equals the same constant we were using before times this charge, and this capital Q indicates the charge of the charge that is causing the electric field. So it is going to be the stationary charge, not the one that is going to be moving. So it's a stationary charge that's causing an electric field, and then the distance to a reference point there. So if I look here at units, it's Newton meter squared per Coulomb squared, because that was the units for the constant, times the charge, which is going to be in coulombs. And so that means that one of these is going to cancel out, and then the distance on the bottom, which is in meters, so that means that one of these will cancel out. And when those cancel out, I'm left with a Newton meter over a Coulomb. And he tells you that those are the units for electric potential. Well, what exactly is a Newton meter? Well, that should look familiar, because if you recall when we talked about work, we said that work was equal to the force times the distance. And if force is measured in newtons and distance is measured in meters, then our units for work are a Newton meter. And we said, oh, well, we're going to define that as being a joule. So electric potential is actually the same thing as a joule per Coulomb. And he never really gives you a good definition for electric potential. So I wanted to give you a definition for that so you can try to start to get your mind wrapped around exactly what it is. So I would recommend that you write this down. The definition for electric potential is this: how much work is needed, and remember, work is done when we move an object. So how much work is needed to move a unit of electrical charge from a reference point to a specific point in an electric field. So basically, if you have a charge Q, and whether it's positive or negative, let's just say that this particular charge happens to be negative, and I have a reference point out here, Q, and I want to know how much work it's going to take to move that from maybe here to here. And so there's a distance that I'm wanting to move it, which I need a distance in order to do work, in order to figure out how much work I'm going to have done. So therefore, the amount of work that I need to move that from here to here or from here to here, that's considered electric potential. And since it says how much work is needed to move a unit of electrical charge, now sometimes this may not be a whole Coulomb, it may be a part of a Coulomb, it may be multiple coulombs. So electric potential is how much work is needed per unit of charge. So that's why this is in joules per Coulomb. He specifies as this is not the same thing as potential energy. Potential energy is only going to be expressed in joules, not in joules per Coulomb. And so I don't want you to get those two confused. He does go to great pains to make that point, but like I said, he doesn't really ever explain to you what electric potential is. So I believe that this definition will prove to be helpful. Also, I have referenced you to a couple of other videos here in the next couple of days of this module where the gentleman does an excellent job of explaining electric potential and electric fields. And so I really want to make sure that you watch those, pay close attention to those, because I think his explanation you will find to be very, very helpful. Okay, we're going to go ahead and work example 14.1 together. So if you don't already have this copied down, you probably want to pause the video for a minute so that you can write that definition down. And then I'm going to make some space so that we can work this first example together. All right, so once again, this is example 14.1. Which is on page 458. Consider a 3.2 millicoulomb positive charge that cannot move. What is the electric potential 45 centimeters from the charge? Okay, so I have here a 3.2 positive millicoulomb charge, and it says that it cannot move. So that means that because this is fixed, it automatically creates an electric field around it, just like we talked about in the last module. And so the question is, if I am at a point out here and I am 45 centimeters away from it, what is the electric potential at that point? Okay, well, in order to calculate that, I'm going to use my formula for electric potential, KQ over R. And so you'll remember that this constant is 9.0 times 10 to the 9th Newton meter squared, squared over Coulomb squared. The charge of this is 3.2 times 10 to the minus 3 coulombs, because remember we need the coulombs to cancel out. And then the distance has to be in meters, so I'm going to change 45 centimeters to meters, which will be 0.45 meters. And just like I showed you before, one of the meters cancels out and one of the coulombs cancels out. And so the electric potential then at that point is going to be 6.4 times 10 to the 7th. And we said, what is a Newton meter per coulomb? Well, it's the same thing as a joule per coulomb. And the unit that we call a joule per coulomb is actually a volt. 6.4 times 10 to the 7 volts. So there's your final answer there. And that is basically what that's telling you, is that to move a full unit of charge, if you had a coulomb charge, to move it from here to here, it's going to take you 6.4 times 10 to the 7th joules in order to do that, if this happened to be a 1 coulomb charge. Okay, so it's a measure of how much work it's going to take to get your reference point to move, or to get your charge, if you had a coulomb of charge, to get it to move 0.45 meters within this particular specific electric field. Okay, so hopefully that kind of, along with the other videos, hopefully that will kind of clear some fog from your mind as far as what electric potential is, and the further we go along, I think it will become a little bit more clear.